Okay, we are doing a math talk. The way that these work is you try to do it without a calculator and without any scratch work. And what we are doing is rewriting each expression as a power of two. So, um, first one is 2 to the third power times 2 to the fourth power. When you think you know what it is, put your thumb up. Once I see a decent amount of thumbs, then I'll know you're ready to move on. So rewriting 2 cubed times 2 to the fourth as a power of 2. Once you think you know what it is, pick your thumb. Remember yet? Nothing there. Oh no, it's not your thumb up. Oh, I'm looking for your guys' stuff. When you're facing on the end. All right, Kalea, what'd you get? Um, I did like 3 times 2. Okay. Does that rewrite this entire expression? Um, for the one I did 3 times 3 times 2 I got 16. Okay. 2 times 3 times 2 and 1. You just got 16. 4. Okay, yeah, this is. All right. So class says this, rewrite it as a power of 2, though. So although this is true, like 2 cubed is 8, 2 to the fourth is 16, and then we probably multiply those together after that to get like the single number. It doesn't want like our final answer. It wants it rewritten as a power of 2. Anyone else think they have it? Aiden, would you get? Okay. Yeah. Wait, that's 64 squared. We'll table that one for a second. And others, any other answers there? Avery, 2 to the 12th power. The other answers? 2 to the 7th power is the correct answer. I can kind of see our thinking on these others, but 2 to the 7th is correct. Macy, how'd you get that? Which is correct. If you have the same base, like base being like the bigger number, they're both 2s. If you have them being multiplied together, you could just add. Okay, guys, let's do our time. Home side, 20-yard line. 20-yard line to us. Well, we were having a good discussion right before the fire grill. What we were talking about is that the correct answer for 2 cubed times 2 to the fourth is 2 to the 7th. And that is because, and you have a little chart of exponent rules in the top right corner. That's because when you have the same base numbers, like these are 2's, being multiplied together, you can just add the exponents. Because yes, 2 cubed is 2 times 2 times 2. That does equal 8, but And then 2 to the 4th is 2 times 2 times 2 times 2, which does equal 16. But if we're now multiplying those groups together, like having it like this, and we learned that repeated multiplication you can condense in an exponent. So like instead of you writing out all those 2's and then counting them, a shortcut, if you will, is this exponent rule that you can add them together. The name of the rule, which is on your chart, is the product rule. So like the name of the rule goes with what's happening between the bases, like applying the bases together. But exponents we can add. Does that make sense? Okay, so then we're gonna kind of skip our normal math talk procedures. Just think about your answer to this one. Think about it, 2 to the 5th times 2, what would that be rewritten as? Based on what we just talked about. Question right. Everyone a couple seconds for the about. 2 to the 5th times 2, rewritten. All right, Kristen, what do you think it'll be? 2 to the power of 6. Anyone think that it should be 2 to the power of 5? Okay, and that's a common thought. There are people that think that because you think, okay, I can add the exponents and there's nothing here, so it must be 5. But really, that doesn't make sense. Because if I have 2 to the 5th power and then I'm multiplying it by 2, it should change, right? Like that number value should be different. If I were multiplying by 1, then yeah, it wouldn't change. We know anything times 1 is just that number. So it is 2 to the power of 6. Because what is the exponent if it's not written? 1. So that is why. If it's not written, it has the exponent of 1. So 5 plus 1 is 6. All right, now next one. Notice it's not going to be the product rule you apply this time because they're not multiplying the bases together. They're dividing them. So what rule should I apply to this one? Say it out loud. The fraction. What's the name of the rule from the chart? Quotient rule. Because quotient is the answer to a division problem. So like when we're dividing the bases, like, but that rule says that if I have the same base number being divided, I can just subtract the exponent. That's what the rule says. So knowing that rule, what's going to be my answer to this one? We've written, Colton? 2 to the power of 3. Because we're doing 2 to the 10 minus 7. Why we do that? Why we can subtract the exponents? Is because 2 to the 10th power is us multiplying 2 by itself 10 times. Okay, so 2 to the 10th power is 2 times itself 10 times. 2 to the 7th power is 2 times itself 7 times. And if we are dividing them, and I have the same thing on top and bottom of a fraction, what happens? What happens when I have the same thing on top and bottom of a fraction? What's 2 over 2? So when I have the same thing on top and bottom of a fraction, it cancels out. So like these 2's could cancel again, again, again. And then I end up with just 3 2's being multiplied. That's why we can do that. quotient rule is kind of a shortcut to doing this. All right, lastly, we have 2 to the 9th divided by 2. Rewritten in should be left. 2 to the power of 8. Because we apply the quotient rule, the bases are being divided, the bases are both at 2. So that says we can subtract the exponents. 9 minus 1 is 8. And yeah, you could type that in your calculator and get what that actual value is, and typically that's what you would do. But for this instruction, I wanted to just do it. All right, so questions on the 1 month. The exponent rules are something that you're supposed to learn in middle school, and then this curriculum assumes you still remember them. So they're all in that little chart. You can refer to that as needed. Typically, as you get into your higher grades, we might like re-explain the 1 or 2 rules that we're using that day, but like otherwise, you kind of expect you to remember. So just keep that in mind. Not all of those on the chart are we using necessarily today, but they all exist. There's exponent rules for all. But today we are on lesson 3, which is representing exponential growth. And we've already been working with exponential growth. We just might not have, like, we didn't attach the definition to it or an equation to it. So we're starting to do that now, starting to do that very slowly. We're going to explain connections between an equation and a graph that represents exponential growth. And then we're going to write and interpret an equation that represents exponential growth. I'm recording right now. I will link it later. I do also include the video from last year, just in case anyone's ever worked ahead. It's the same lesson. Or like for things like today, like the fire drills, so our lesson's going to be shorter. If you want more examples, watch the one from last year. I also have one that is quite different, but does have a lot more examples in a different format. So both are really great. I'm sure you can also look up yourself in YouTube, any subject, and get a video that's already made to help you understand it better. That's what it's for. The practice is in Schoology. We are supposed to have a quiz today. We'll see. I think it's easy enough to do in a short amount of time, but we'll just see. I feel like we can get through what we need to get through very fast. See. Especially if we do it mostly together. So we're going to move on to this next activity. Complete the table. Take advantage of any patterns you notice. So look at the patterns, and we'll give you more than that right now. Then you have a couple equations where there's a question mark. So there's the part of it that's missing. You have to be able to tell me what it should be based on what you know about the exponent rules. And then answer what's the value of 5 to the power of 0 and 2 to the power of 0. I'll give you like 2 minutes just to try to answer those yourselves before we have a group discussion. Okay, who thinks that they filled out the table correctly? Based on the patterns you noticed. All right, nobody? So what is a pattern we can notice? Sometimes we're not looking for like something crazy. Sometimes it could be as simple as the x's are decreasing by 1. That's a pattern. Do we see any other patterns? or notice anything else that's different than what we normally see? Raw. Okay, so in this output column, to go from 81 to 27, I could divide by 3. Now, also something to notice, I think sometimes we get so used to it being a certain way that, I don't know, we missed that it actually had the rule here for how they're getting the outputs. For each output, they're doing 3 to the power of whatever x is. So you guys all could have put it into it because of the rule. But 3 to the power of 4 is 81. 3 to the power of 3 is 27. That is the rule. But also, if you were to continue this pattern that Merle noticed of dividing by 3, what is 27 divided by 3? And guess what? 3 to the second power is 9, right? What's 9 divided by 3? And what's 3 divided by 3? So 3 to the power of 1 is 3. 3 to the power of 0 is, that's 6. Questions, that makes sense. See that. Now you had to find the parts of the equation that were missing in the next one. So for example, and that's kind of similar to our warm-up, except they're replacing something else. They're not asking what it rewrites to. But knowing what we know from our warm-up, if I have 9 to the power of something times 9 to the power of 7, and it equals 9 to the power of 7, what must that something be? What should the question mark equal? What exponent rule can we apply? Amy? Okay, so the question mark, if it were 0, let's see, does that work? If I were to make it 9 to the power of 0 times 9 to the power of 7, does it equal that? Well, if you apply your product rule that says you can add the exponents, Tristan, stand up. 0 plus 7, does that equal 7? Yes. So that is correct. The question mark should be 0 for that one. Also, if you weren't sure, you could have typed in your calculator to check. Like, for example, someone earlier thought it should be 1. Well, if I did 9 to the power of 1 times 9 to the power of 7, and then in a different cell, I did 9 to the power of 7. Those are not the same numbers. But when I do what you guys said in here and change that to a 0, now they're the same. Okay, so that does have to be 0 for that one. Now for 9 to the power of 12 over 9 to the question mark, equaling 9 to the power of 12, what does that question mark have to be? Tristan? 0 is correct. Because that rule, the bases are being divided, so you would use the quotient rule. You're basically asking yourself, 12 minus what gives me 12? And you say 12 minus 0 gives me 12. You can check that in the calculator too. But questions on that? All right, last one from this set. What's the value of 5 to the power of 0? What is it? 1. And how do we get that? Amanda, use a calculator. Rules. Okay, one of the rules on that little chart that was given to you is the zero product property. Is it product? Zero power rule. Or zero exponent. Sorry, confusing my front. So zero exponent rule is the one that's from your chart. And that's the one that says any number to the power of 0 equals 1. Any number to the power of 0 is 1. So what's 2 to the power of 0, class? What's a million to the power of 0? What's negative 1 to the power of 0? 1. And you could check in your calculator. I mean, if you put a negative, you might have to put it in parentheses for it to work. Yeah, it needs, the number would need to be in parentheses. That's why I always tell you, like, negatives, put them in parentheses. But anything to the power of 0 is 1. If you ever forget that, try it out in your calculator. Okay. So good on that. You still have one more example to do. I don't know if we'll have time to do things. We'll just keep going. You'll take it eventually, but just maybe not today. All right, moving on. So why is that relevant? Well, we've been talking a lot about exponents, and this unit is exponential functions. So you've learned about linear functions. You can tell me all about how linear functions look, what their equations look like, how to identify them from a table, how to answer problems using them. You're going to be able to do all of those same things, but now with exponential functions. Starting with this activity, which is similar to what we've been doing in the past couple days. So in biology lab A, 500 bacteria reproduce by splitting. Every hour on the hour, each bacterium splits into 2 bacteria. We're going to complete the table. We're going to write an equation relating N, the number of bacteria, to T, the number of hours. And we're going to use our equation to find N when T is 0 and what the value of N means in this situation. So I want you to try that right now. Try filling out the table based on how it's reproducing. That number is either increasing or decreasing. And then be able to make an expression so that no matter what hour we want to look at, we can get an answer that is correct. Give you maybe 3 minutes to try that out. So remember, the bacteria reproduces by splitting. So every hour on the hour, each bacterium splits into 2 bacteria. So table 6, if we started with 500, how many will we have after 1 hour? Table 6. 1,000. Some people get hung up on the word splitting, like, yeah, splitting is normally dividing, right? Like it still is. But what's happening is the number of bacteria is increasing. So if each bacteria splits into 2, we're basically doubling the amount that we have currently. So then table 7, if I have 1,000 in hour 1, how many do I have in hour 2? Table 8, how many would I have in hour 3? Table 9, how many would I have in hour 6? 32,000 is correct. If you thought 8,000, it's because they are missing some numbers right here. So again, I mentioned before, like we get so used to things being a certain way that we kind of like are blind to it when it changes. So yeah, in hour 4, there would be 8,000 because it'd be doubling from 4,000. In hour 5, how many would there be? And that's why in hour 6, there's becoming 32,000 because it's a 16,000 that's. All right, good. Questions on that? So if it were me and I needed to find out, like maybe this was the problem and it said how many bacteria would there be in hour 6, I might just continue the pattern this way because honestly, I didn't have to do it that many times. But there have been tests that said, how many would there be in hour 100? And that's just unreasonable to keep that pattern going. So that's why we would like for there to be an equation or an expression to find it for whatever hour. All right. When we are making that, think about the math that we're doing to get every single one of those answers. Let me move this to the side. So I can show you. All right, but think about the math that you did when you went from 500 to 1,000. What math did you do? And what did you multiply? By. Or you multiply 2 by 500. Right? Isn't that what we did? And then what did we do to get 2,000? We did 1,000 times 2, or in other words, we did 500 times 2 times 2. Because this right here was 1,000, and then we're timesing the 2 again. In this one, what math did we do? Okay, great. And then in this one down here, I'm hoping guys, like I'm giving you a way that you can understand. I feel that so often math is like, these are the rules and you just need to follow them. This will help you when you forget the formula, say like on your state testing. As well as you make it because we've done it like in a way that it's really easy, in my opinion. But then when we get to this hour, what math are we doing to get that one? Okay, good. Whenever you're having to make the expression, what is staying the same, what is constant, should be a constant in your problem. So like, in every single one, I had to consider the 500 that we started with. So that should not change. I am multiplying it by a factor of 2 in every single situation, right? So in my expression, I should have times 2. But what's changing each time is how many times I am multiplying by 2. So how can I incorporate the t in there? Listen. Have the t as the exponent. And remember, we could condense these like repeated multiplication of the same number with an exponent. That is what's changing these times. Now I have an expression for any hour. And I don't have to like continue the pattern of running times together. Questions on that? Okay. I'm gonna give you kind of like a definition right now, so it's really important you put it somewhere. Yeah, put it. We're not gonna end up doing the graphing, so if you could put it like towards the bottom, that's fine. But the way that you know linear is y equals mx plus b, you need to know that things with an exponential pattern, like multiplying the same amount each time, has a formula that looks like this. I'll put 2 ways of writing it just so that whether you like using x for input or t for input, since time is normally your x anyway. These are gonna both end up meaning the same things, but y would just be how many you have for whatever the situation is, like your output. A is gonna be your initial amount, whatever you're starting with. In this case, we started with 500 bacteria. Write it down. We'll be multiplying it by, we usually use the letter B, but what it stands for doesn't even start with a B. It stands for common factor. So B is what you're multiplying by each time to get the next number. So what's my common factor in the bacteria problem? 2. That's what we multiply by each time. And then T is for time. T is time. Just like how X is normally time. Anyway, you could use a T so that you remember. However many hours, however many days, or whatever the situation is, they're putting that as the exponent. All right. Last little thing we'll talk about. We're obviously not taking the quiz today. So last little thing we'll talk about on this one is, so this is a different lab. They have a different equation. They didn't give you a table, they just gave you the equation. So in lab B, they produce single cell parasites, and they also reproduce hourly. An equation that gives the number of parasites P after T hours is shown here. Explain what the numbers 100 and what 3 mean in this situation. All right, so based on this little definition I just gave you, that 100 is what? What position is it in? Is it 100 hours? Is it 100 parasites? Is it 100 that they started with? Is it 100 that they're multiplying by? What does this 100 represent? The initial amount of parasites. Because they want to measure every hour, like how fast they're reproducing. At hour 0, that's how many they have, right? Because if I did 100 times 3 to the power of 0, we just learned anything to the power of 0 is 1. So it's like 100 times 1. All right, now what does that 3 mean in this situation? It's our common factor. So in simple terms, maybe people don't know what a factor is. How are these parasites growing? Are they doubling? How are they growing? Are they growing faster than the bacteria? Yeah, because the bacteria common factor was 2. If I multiply by a higher number, it's growing faster. So how is it growing by in simple terms? It's tripling each time. The number of parasites is tripling for every hour. And that's all we got to in my first hour, so I think it's a good place to stop. Obviously, we're not taking the quiz, but you have 6 minutes. You're going to just be sitting waiting for this. Any questions?